Okay, let's get started. So, okay, so let's start. Okay, so today we will go over, hopefully you all know the proof of multiplicative group of a field is cyclic. So we're going to move on to factorization. Factorization over a field. Right, so recall so now, I mean, we already sort of went over this, but now the question is, what if you can't factor anymore? Right, so we're going to define what an irreducible polynomial is. So a non-constant polynomial f of x in, say, f of x is irreducible over f. Or i.e. we say is irreducible polynomial. If f of x cannot be factored, or cannot be expressed, I guess the book says expressed as product g of x times h of x of two polynomials, g of x and h of x, both of lower degree. Than degree of f. So if you look at it this way, right? So let me give an example. Is this irreducible in, say, q of x? Okay. Now, what about this? So this is yes. So look at the definition. I see for some people it's not automatic. Yeah, this is yes, right? This is still irreducible. So, because if you think of how would you define irreducible over z, right? It means you can't factor as or prime in z, you can't factor as product of two non-units, right? So it's similar here, right? So in Z, like, sure, you can factor 3 as 3 times 1 and negative 3 times negative 1, right? But these only differ, these differ by like these terms like 3 and negative 3 and 1 and negative differ by multiplication by a unit, right? In this case, the unit is negative 1, right? Remember, what's a unit? It's is whatever has a multiplicative identity, right? So yeah, all polynomials of degree 1 are irreducible. So like, right? So the units here are negative 1 and 1, right? Because these are the only invertible stuff in Z. So if I try to state this here, right? I can't factor f of x as product of two non-units, right? Two non-units. So one of them has to be a unit. Well, the first question is, what are the units of f of x? Can anyone tell me? It was somewhat like your quiz question, the quiz free response question, except I changed f to like z mod 5z. So what are the units of f of x? For f of, let's just say f is a field for now. Yeah, let's make it easier. Yeah, and like, what are the units of f, right? It's just f without 0, right? Everyone agree? So this and this, well, yeah, like they're two different, but like, yeah, you could factor this as like 3 times x minus 2. It's still irreducible because this thing's a unit, right? Like I can't factor, like I can't factor 3x minus 6 as product of two non-units, right? Like I can only factor it like this, right? But the problem is this is a unit, right? Because remember, using what I wrote here, the units of Q are units of Q. Since Q is a field, it's Q without 0, right? Units of Q of x. It's Q without 0. And 3 is certainly in Q without 0. So 3 is a unit. So you see here, you can certainly factor it as this, but you can't factor it as product of two non-units, right? Okay. Is everyone clear on this? So now you see why it has to be like strictly lower degree, right? Because if you had something the same degree as f, well, it could differ by a constant, but that constant is invertible in your field, right? So it only differs by a unit. No. Just take this definition. I mean, I'll put this in quotes, but I'm saying I'm saying that this is how you should think about it. Yeah. Yeah, take the definition given the book. It's correct. So, but I'm just saying you might wonder why you need strictly lower degree, right? So I'm sort of explaining to you why, like, right? Because this thing certainly factors, but this thing is like the same degree. So you're like, does this count? And then yeah. Everyone clear on this? Yes, no. Okay. So now the second issue is you should be careful about the definition, right? So here it's over f. So what do I mean by being irreducible? You can't ask me like, is this irreducible without telling me over what, right? Like if the book doesn't say, it's probably whatever like the base field is, right? Sort of implied, but normally like if I'm asked you, it's either implied that if they don't say, it means over the same place you're working with, or it could be over another field, right? Like if I ask you, like, is x squared plus 1 irreducible? If I choose two fields, like over R, right, over C, this matters, right? Because like over R, this thing is irreducible, right? You can't really factor it as like a product of things, but like over C, right, this is just x minus I, x plus I. So of course, this is like, yeah. Does everyone understand? Like you need like this part. It's pretty important. Okay. So with that, okay, so hopefully we all understand definition of irreducible. So I could move on. So the first thing is, how do I figure out whether something's irreducible? Well, there's an easy criterion for low degree, right? By low degree, I mean 2 or 3, right? So if f of x is in f of x, and, you know, instead of n, I'll just say is degree 2 or 3, then f of x is irreducible over f, if and only if it has 0 in f. So the only thing you need is the fact that if f has a 0a, then x minus a is a factor, right? So that's really all you're using, right? Because if you had degree 2, well, I need something of low degree, right? So I have two choices. I have degree 0, degree 2, right? A product of a degree 0, but this can't happen because degree 0 is a unit, right? So I mean, it also can't happen because like this is of the same degree. So this is a no-no. So the only other choice is degree 1 and degree 1, right? Since we're in the degree 2 case. But a degree 1, it just means that there's a 0, right? I mean, from here. Does everyone agree with this? Because if you're degree 1, well, then you're bx plus c, where b is not 0. Because if b of 0 is 0, it's not degree 1. So since this is not 0 and you're over a field, then b inverse. So b inverse exists because you're over a field, right? So that means, you have a 0. That the 0 is c b inverse, right? So to be a little, sorry, it should be b, yeah, sorry, cb. Did I do this correctly? Hold on. No, what am I doing? Okay, factor out b. So this is b in, this looks more correct, right? Okay, so same for degree 3, right? Degree 3, you have 3 choices. You have degree 0 and degree 3, but this would mean it's not, so like, oh, sorry. No wonder I look a bit confused. Is it just, it has no 0, no 0 in f. or else it's irreducible. Okay, so here, right, in this case, it would be, yeah, I don't know why I was like so confused. I was like, the statement just didn't look right. Okay, so here, right, obviously, this would be irreducible, right? So it would be reducible. So this would mean it's reducible in this case, right? Because it splits the degree 1, degree 1. So here, you can either have degree 1, degree 2, or degree 2 times degree 1, right? In either case, right, these are the cases where you are reducible, right? But in either case, you have you have a degree 1, in which case you have a 0, right? So now in degree 4 and higher, it's possible to not have zeros, but still be irreducible, right? I mean, and still be reducible, because you can split to like degree 2 times degree 2, right? And in fact, it gets worse for high degrees, right? You get like degree 6 could be like product of 2 cubics. So on and so forth. Is everyone clear on this? Yes? No? Seems pretty basic. Okay, so that's like an easy case for like degree, degree 2 and 3. So now what about like, over z or q, right? So what about that? Well, there's a theorem where we say if f of x is in z of x, right? Then f of x factors as a product of two polynomials sorry, if as a product of two polynomials of lower degrees are, yeah, I don't like the notation of the book because they use R and S, but lower degrees R and S. So I'm gonna use this. I'm gonna just of x in Q of x. If and only if it has factorization with polynomials of same degree R and S in Z of x. So this is, it's pretty, it just means if you could factor over as like linear factors, I mean, not linear, but like factors over Q, then you can make it over Z. So an example would be like, if I could factor f of x, let me just show an example as like x minus, let's do an example like a over I don't want to use the same one. A over b x p over q times what are two good letters? C over dx minus e over f, right? So if you could factor it as over q, then like you could have a same factorization of the same degree over z, right? You just clear denominators, right? You just make it like, you just multiply by like bq df, and then you have a q df x minus p BDF. So these are all integers, right? So these are rational numbers times, whatever this is, C times BQFX minus E BQD, right? So again, this is of the same degree, right? This is still linear. This is still linear, right? But now this is in Z of X, right? This was originally in Q of X. So so this is sort of saying if you are reducible over Q, then you are reducible over Z. Is everyone clear on this? The proof is just really clear denominators. Like it's not that. Of course, right? This is as it doesn't have to be linear, right? It could be like quadratic, right? But in either case, it's finite. You just clear all denominators. I don't have one at the top of my head, but like, I would have to think. Yeah, I mean, like, just factor out a 2. So it factors as 2 1/2 x minus a half x plus 1. So this factors as, like 2x plus 2, right? So these two elements are in Q of x, right? So if you like, let me erase this. These two elements are in like Q of x. I mean, this is in Z, but if you're in Z, you're in Q of x, right? So it's saying if x squared minus 1 can factor like this, then I can clear denominators to make it factor like this. If that makes sense. Like, I mean, yeah, so, but we don't really care about this, right? So what we care about is the contrapositive. So what's the contrapositive say? Like if P then Q, what is contrapositive? Sorry, this is not the Q, it's normal Q. So basically the contrapositive is what we care about, because we say if irreducible over Z, then irreducible over Q, right? Because what's the contrapositive? It's not Q. If not Q, then not P, right? Everyone remember what contrapositive is? So this is nice, right? Because now like to basically, so if I had like a degree 2, right? I mean, it's still a bit hard. I mean, like basically, if I had like a degree 2, f of x in z of x, right? All we had to do is check there's no zeros, right? But if the question is check irreducible over Q, right? So I can't factor it as two things as linear factors over Q. Well, that's the same. Instead of doing that, I just need to check irreducible over Z, right? Does everyone see how powerful that is? So now, like, we had a theorem that says, like, right, if we're degree 2 or 3, we just need to check there's no zeros. So here, instead of checking there's no zeros over Q, you just need to check there's no integer that gives zeros. Like, hopefully you all see like the power of that. right? I mean, checking irreducible over something smaller is always easier, right? Because like, you know, like I said before, right? If this was irreducible over R, this is certainly irreducible over like Q, right? Because if you can't split it as, you know, polynomials in real numbers, since Q is a subset, you can't do it over Q, right? But this might, you know, you would think like, what about irreducible over like the opposite, right? If you're irreducible over R, are you irreducible over like the bigger field? And that's not in general true, right? At least here, we know that, you know, so that's why this is strong, because it's saying like, to check irreducible over something bigger, we need to check irreducible over something smaller, right? So yeah, that's really powerful. I think let me just say, yeah, it's only for Z and Q, sadly. It's not true here, right? To check it's irreducible over C, I can't just check it's irreducible over R, right? Like R is in C here, Z is in Q, right? So here, to check irreducible over here, I need to check irreducible over here. But this is certainly not the case, right? If it's irreducible here, it doesn't need to be irreducible here. Like it splits, right? So that's why I'm saying like that this is pretty powerful, because like it's in general, it's just, this is just not true. Like, yeah, it has to do with the fact that Q is just, you know, field of fractions of Z. So let me just say this. I think this is called Gauss lemma. Don't you know, if you want to look it up. I don't know why it's a theorem in the book. I think it's called Gauss lemma, if I remember correctly. Something like that. Okay. Everyone clear on this? Yes? No? Okay. This one, I'm not gonna go, you know, too deep. You all learned this in like, you know, some other class, probably rational root test. Hopefully you all know this. If P of X is an x to the n plus, you know, a0, but an not equal to 0, a0 not equal to 0, then every root in Q is of the form. So this won't help you entirely check it's irreducible, but at least it'll tell you whether there's a 0, right? So is of the form P over Q, where P equals plus minus factor of a0, Q is plus minus factor of an. Yeah? Is everyone, do you all know rational root tests? I'm sure you've all heard of this before. Like, yeah. So hopefully I just need to write the statement down. But let me just test you really quick. Why do we just without loss of generality assume this? So first off, if a0 is 0, I can just factor the x, right? And then just consider the new thing, right? Like if this was like x to the 5th plus x to the 4th plus x cubed plus, right? So this is like a1. So if a0 was 0, then I could just factor the x out and then consider this new thing, right? Where the a0 is not 0 now, right? Just work with this polynomial, right? Because in this case, we just know, we already know x equals 0 is a 0, right? So does everyone understand, like without loss of generality, like we can just assume this, right? This is like the constant term. Because if constant term is not 0, you know 0 is a root, in which case you just factor it out, right? And this is, just to avoid redundancy, right? Like nobody writes this, right? Like nobody ever writes, like, I'm sure you all just write this, right? Nobody like includes 0 as like the constant term of the leading coefficient, right? So I mean, this is like this is more like without loss of generality than but like, yeah, okay. I'm gonna move on since you've all heard of this. I don't think this is anything new. So the more important thing is now, what about over ZP? Right? You could certainly ask whether you're irreducible over like a finite field, right? So if you like Z mod PZ. So Eisenstein, there's something called Eisenstein criterion. So this is pretty powerful. I'm sure your professor will prove this, or he did. Let P be in Z a prime. Suppose f of x is equal to an x to the n plus dot plus a0, right? Is in Z of x and an not congruent to 0 mod p. Yeah. So in other words, an not congruent, and then ai congruent to 0 mod p, and a0 not congruent to 0 mod p squared. So if all of you don't like this assumption, another way to write this is P does not divide an, P divides ai for all I not equal to n, and P squared does not divide a0. Yeah. Yeah. Okay. So I guess instead of I not equal, I could just do I less than n. So from here, right, what does it say? Well, then it says then f of x is okay. I'm gonna say over q, but the proof is work over z mod pz. Yeah, it's q. Using, I was to say using finite fields. Then f of x is irreducible over q, because I mean you're still in characteristic 0. But the proof involves reducing this equation mod p, which in other words means work in z mod pz, and then basically derive a contradiction using these statements. So why is this powerful? Well, now if I ask you this, you can use Eisenstein. So let me ask you, is this irreducible? X to the 100 plus 3 to the 34. So this is 3 to the 34th power. Yeah. I don't know. 432 x to the 32nd plus 3 to the 1000 x plus 6. So is this irreducible or not? I made it pretty explicit. So yeah, see, if you just saw this without knowing this criterion, like you would be like, man, like how, I mean, because if you just think of factoring, there's many ways to factor it, right? It's degree 100. So you could make it could be like maybe a factor of, degree 50 times degree 50, or degree 49 times degree 51. There's so many options, right? But here, you just use Eisenstein criterion. You take P to be 3. Yeah? So this is certainly in Z of X, irreducible over Q. Yeah. So you certainly, 3 divides, 3 does not divide this, right? 3 does not divide AN because AN is 1, right? 3 divides this term, 3 divides this term, 3 divides this term, 3 divides this term, and 3 squared does not divide this term, right? So from here, it's irreducible by Eisenstein. Hopefully you can see why it's so powerful. No, this is in Z. Yeah, you could choose any prime, exactly. Yeah. So like here I'm choosing my prime to be 3. Yeah, nobody's saying like, P is fixed, right? P is just some prime. So if another prime works, I mean, in this case, the only prime that works is 3, because I made it that way. Irreducible by Eisenstein criterion. Everyone clear on this? Yes, no. Okay. So let's just do like 2 more questions and then we could call it a day. So let's do some examples. How about this? Find all irreducible degree 2 polynomials in Z mod 3Z of X. So again, when the book, says irreducible in here, right? And they don't really say irreducible over what, they sort of implied they mean over whatever the base field is. So all irreducible over, so sort of implied it's over Z mod 3Z. Yeah. So how would you do this? So without loss of generality, right? How does a general degree 2 polynomial look like? Looks like what? Like, just use variables. Like, how does it look? How does a regular degree 2 polynomial look like? Mm-hmm. Yeah, I'll just use ABC. So, but where A is not 0, right? Agree? Because if A was 0, it would not be degree 2. So you can see the first thing you could do is, well, we could simplify this. We could factor out the A, right? Because it's not 0, there's an inverse, right? So does everyone agree, like, this being irreducible is the same as this being irreducible? Does everyone agree? Because like this is just a unit, right? Everyone clear on that? So really we could reduce the case, right? Reduce to case where our polynomial looks something like this. Everyone agree with that? Yes or no? Where B and C could be anything, right? I mean, where C is in, I mean, it's just anything in Z mod 3Z of X from above, right? From here, we can sort of reduce to this case, right? Okay, now tell me all the possible combinations. Right, we could have B is 0, 1, 2. C is 0, 1, 2. Agree? So I have 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, and then 2, 0, 2, 1, 2, 2, right? So when B and C are 0, right? So for 0, 0, let's write it out, right? When B and C is 0, it's x squared. When B is 0, C is 1, it's x squared plus 1. When B is 0, C is 2, it's x squared plus 2. 1, 0 is x squared plus x. 1, 1 is x squared plus x plus 1. 1, 2 is x squared plus x plus 2. And finally, when B is 2, right, it's x squared plus 2x. 2, 0. Oh, sorry, 2, 1 is x squared plus 2x plus 1. 2, 2 is x squared plus 2x plus 2. Does everyone agree that these are all the possible, at least different degree 2 polynomials? Okay, well, tell me, is this one irreducible or not? Can you factor x squared? So again, you can use the fact that it's degree 2, right? So you can use the fact that it's irreducible if and only if it has a 0, right? In this case, there is a 0. It's 0, right? In fact, you know what it factors as, right? This one is reducible, right? Because you can factor it as like x times x, right? So what about this? So all you need to do is check whether there's a 0, right? So so you only need to plug in 3 points: 0, 1, and 2. 0 squared plus 1, that's not 0. 1 squared plus 1, that's 2, that's not 0. 2 squared plus 1 is 5, that's not 0, right? So this is irreducible. Now, what about this? 1 squared plus 1 squared plus 2 is 3, that's 0. So this is reducible, yeah? And same thing here. I mean, this is clearly, there's a factor of x here. Here, 1 squared plus 1 is 3, that's 0, right? Here, 0 works, 1 is fine. Let's try 2. 2 squared is 4, plus 2 is 6, plus 2 is 8. 8 is not 0. So this is irreducible. This is not. So 1 is fine here, right? 2 is 2 squared plus 2 is not fine, right? Because 2 squared is 4. So 4 plus 4 plus 1 is that's 0. And then here 0 is fine, 1 is fine. Yeah, it seems that this is fine, right? So really our only irreducibles are x squared plus 1, x squared plus x plus 2, and x squared plus 2x plus 2. Does everyone understand this question? Yes? No? Makes sense? Okay. Well, let's do one more. So this one should be easy. Example, show x to the p plus a is reducible in z mod pz. So again, if they don't write it, they mean over whatever this field is or domain is. So show this is for a in z mod pz. So let's do the easy case. If a is 0, then this is just x to the p, right? This is p prime. So x to the p is reducible, right? I mean, it factors as p times, right? So that's easy. So what about a not 0? Any ideas? So let me give you a hint. What is this? X plus a to the p. What does binomial theorem tell you? Yeah, if you like, minus 1a, p choose p, a to the p, right? But these are all 0, right? All the middle terms are 0 because p choose 1, p choose 2, that has a factor of p in it, right? And over z mod pz, that's 0, right? So this is 1, this is 1. So this is x to the p plus a to the p. Does everyone agree with this? Okay, so can you all conclude the result now? What's the next step? You all learned this. So what does Fermat-Little theorem tell you? If a is not 0, what is a to the p minus 1 congruent to? 1 mod p. Good. So if I multiply by a on both sides, I get this. So now you see this is reducible, right? Because x to the p plus a factors as x plus a to the p. And this is certainly reducible, right? It's just x plus a, p times. It sort of generalizes from here. Sorry, this is Fermat-Little theorem. Yeah. So yeah, so these are some questions on reducibility, irreducibility. So I'll go over whatever the next section is on Thursday. So yeah. Okay, that's all I have for today. Yeah, I'll see you all Thursday then.